Hi everyone, and welcome to the very first lecture on converter circuits. Today we're going to be talking about single quadrant switching circuits. Just to go over a little bit about the content, I plan to talk about switch applications in single, 2, and 4 quadrant converters. So today we're only going to talk about single, but yeah, that's for the future. And then we're going to talk a little bit about things in ECE 255, and that's like if you've never taken ECE 255, you probably covered it in ECE 2001. And if you're not electrical engineering, it's pretty much about power semiconductor devices, like power diodes, MOSFETs, BJTs, IGBTs, and thyristors, stuff like that. And then we're going to talk about switching losses, the cases like where a transistor switches with a clamped inductive load, straight capacitances and inductances, pretty much just how efficiency is related to switching frequency. So this is where I'm going to pause the video. I'm going to do this in the future just so I can like draw stuff, and then we'll continue. Okay, so we're going to talk about the single pole, single throw types of switches. And over here, I've drawn that. This is the SPST switch. And this is kind of taking an example of the buck converter. We have the SPDT switch where D is double throw. D is just double, I mean. So this is single pole double throw switch. And this is how it's conventionally drawn for convenience, but we're going to be replacing it with the SPST switches. So this is important that we're replacing this with two switches, two different switches, by the way, just so that when it's in this form, then you can replace these switches with a semiconductor power device. So in the first case, in the SPDT, you have two possible positions of the switch. So the switch can be in position 1 or could be in position 2. But in the second case, there's 4 cases, right? There's 2 more cases than in the first one because now you have 2 switches. You can have when they're both on, when they're both off, or when one is on and one is off, and the opposite. So when both switches are on and you turn them on at the same time, you can possibly destroy the switch because you're shorting out the power source and there's a very large current around the loop there. And then you're going to have a lot of power loss. And we have to make sure that this doesn't happen ever in our drive circuit, even for a few nanoseconds. And then when both switches are off, then the characteristics of the converter completely changes. And that can lead to things like discontinuous conduction, which we can talk about later. But pretty much there's adding another switch obviously complicates more things and makes it more complex, but then it also makes it easier for us to use power devices. So now we're going to be talking about quadrants of SPST switch operation. So on the x-axis, we have our off-state voltage, which is imposed on the switch by the converter when the switch is turned off, which is also called blocking voltage. We'll go more into that later. So we're going to ask ourselves, how much voltage does the switch have to block when it's turned off? And that's either given by the input VG, which I should have defined up here, which is the voltage from the generator, or the capacitor voltage in the converter, or the output voltage. But mostly it's going to be given by the input. So how does the voltage change polarity? So this will affect what switch you're going to use. Not what switch you're going to use, what power converter device you're going to switch the switch with. I don't know if that makes sense, but we'll explain that more. And then on the y-axis, we have the switch on state current. And that is the current imposed on the switch by the external converter or by the converter itself when the switch is on. So that is given by the inductor current or some combination of the inductor currents. And it can also be a function of the duty cycle or a function of the load current. So in this case, I've highlighted the region where both are positive, where both the state current of the switch and the state voltage are both positive, and that will put you in the first quadrant. Yep. So you can use switches in, like I said before, the single, 2, and 4 quadrant switches. And in the first case, you have this one. You have the single quadrant switch. And this cannot, not just only is in the first quadrant, but can be in the second and third as well. I should have numbered this stuff better, but yeah, so you have 4 possible combinations here. It's not just this first quadrant. And then we also have the current bidirectional 2 quadrant, where you have 2 possibilities depending on the blocking voltage. So remember that if we look up here, our uh, our variable on the x-axis is the switch off state voltage, right? So you have the current and your voltage there. So in this case, the switch must conduct both positive and negative currents. So that's why we're both here and here. But it has to block positive voltage when it's off. So that's why it's only on this side. Oh my gosh, I should be using different colors. That's why it's only on this side, right? So that's the reasoning behind the positioning there. And similarly, in this case, the third case, you have the voltage bidirectional 2 quadrant where you have 2 possibilities, right? It could be here or it could be here. So this is where you have only one polarity of current, and then you can switch your blocks between the polarities of voltage when that's off. And then you have the most complex case, and obviously the most general. It's the hardest to control and realize with semiconductor devices, obviously, because you can be operating however it wants. It could be the case 1, 2, or 3, or it can be operating with all the quadrants. So especially in AC to AC devices, you're going to need 4 quadrants. It can block positive and negative voltage when it's off, and it can conduct either positive or negative current when it's turned on. So let's talk about what kind of switches we have in the single quadrant. I redrew how we're defining our voltage and current here. So if the on-state current and the off-state voltage are of one single polarity, then we have a single quadrant switch. So we have active switches, which decide if we switch our states on or off. And that is controlled by a third terminal called the control terminal, which can be realized with a gate of a MOSFET or an IGBT. And at any given time, we can know the conducting state. Know the conducting state. The switch by the control signal that we can apply to it. And then we have passive switches. And they're controlled by converter waveforms that are applied. So if the converter voltage or the current forward biases the diode, then it will do that, and then the switch will be on, for example. And then we have a really special case, which is the SCR, which stands for silicon controlled. Oh, wow. Fire. This is a really special case, but it's turned on with a control signal, so the turn on transition is active, but once it's on, it behaves like a diode. So this means that it won't turn off until the external circuit or the power converter circuit reverse biases the SCR by itself. We don't have to really focus on what kind of switches we're using at this moment. This is just the different kinds that you can use in single quadrant. So now we're going to talk about diodes. I love diodes. In this example, I have on the x-axis our voltage, and then on our y-axis I have the current. This is really a review of what you're going to have as the IV characteristics that you probably learned in 207 or 2007 or whatever you took. And we're going to go see the classic exponential characteristic. It's going to look like this. And I'm kind of ignoring the forward voltage drop. Just in this ideal case, we're putting the characteristic right along the axis. So when it's on, it's going to conduct positive current, and then when it's off, it's going to block a negative voltage. And the off-state voltage, When the off-state voltage is negative and the off-state current is positive, then it'll be in the second quadrant. And then you can realize it with this, the diode. And if you have the voltage in the opposite direction, then you can, then the operation will be in the fourth quadrant. And then the diode, you can be connected in the opposite direction that way. I think I just need to illustrate what I mean when I'm saying this. So I'm just going to draw a quick graph. So this is your current, right, and your voltage. So then when it's this specific polarity, which is in this case, now you're in the second quadrant. But if your diode is defined like this, and your current is going up, then you're going to be in this quadrant. Time for BGTs and IGBTs. That stands for the bipolar junction transistor and the insulated gate bipolar transistor. I'm not going to talk too much about these because usually MOSFETs are used more often in industry now. But when the devices are on, they are operating at a kind of a low voltage and a positive current. And when they're off, the characteristic tends to be over here. So they're going to block positive voltage there. They're not really capable of blocking significant negative voltage. So I believe their characteristics will look like this. Ooh, yeah. So that's kind of why they're not used as much now, but there's definitely an application for them, but I'm just not sure how they're used in transitioning in industry at this moment. Now we finally get to talk about MOSFETs. MOSFETs are metal oxide semiconductor field effect transistors, a mouthful. It's an active switch and it's controlled by a terminal C. And this is normally operated as a single quadrant switch where it can conduct positive on-state current or negative current here, and when it's operating in the reverse circumstances. So it can block off your positive voltage and it acts as a body diode, which means that uh, it has a built-in diode that comes from shortening the substrate of the MOSFET. Shorten the substrate of the MOSFET to the source of the MOSFET, which adds an extra PN junction. So this is essentially a diode in parallel with the MOSFET channel, and that allows it to also conduct a negative current. So this can actually act as a bidirectional device in some applications, even though I defined it as a single quadrant switch, but it's not that efficient because it's slow a bit in the reverse direction, but there is a lot of industry applications for this here, but I'm not too sure about it. So if you guys find out where MOSFETs are used in this reverse application, please let me know. Because the way that you turn on the reverse circumstance, you have the potential to destroy your MOSFET. So you have to be careful of that. And so in conclusion, if the on and off states are on the IV characteristic of this MOSFET, then the switch can be realized with it. Okay, this is going to be the last section of the lecture. Pretty much what I've been talking about this whole time is kind of the different kinds of switches, different kinds of semiconductor devices that we can use to replace these switches. So let's take an example. How are we going to use the information that we have about our circuit in order to create a new circuit where you can replace the switches with semiconductor devices, right? So we have to think about this. How can we realize this in terms of MOSFETs and diodes? What is the on current? What is the on state current imposed on each switch by the converter? And then what is the off state voltage? Okay, so let's take this one step at a time, right? So let's do switch A first. Switch A. So the way you do this, you have switch A first on, and then you turn B is off. Turn B off. So from analyzing a buck converter circuit, or normal 2001 201 circuit analysis, when we turn B off, we know that the current that switch A is conducting is the inductor current here. When B is off, this is open and the switch is conducting the same current as IL. So we know that IA equals IL. And we know that this is also the load current. So this is not found out just by looking at this. This is how the buck converter works. So we know the I load can be computed by, oh, I'm so sorry. I'm doing V over R, where V is D, which is your duty cycle, times your voltage at the generator over your R. So let's assume all these are positive. Your duty cycle is positive. Your voltage, your R is real, right? So let's say IA is positive, greater than 0. Okay, so then let's switch A off. Then B is now on. Oh, I just wrote the same thing again. Is on. Okay. So then we have let's look up here. We have our VA equals VG, and we define that as greater than 0 because VG is greater than 0. So we know that this is having a positive operation in quadrant 1. So we can use a transistor like in IGBT here. So this is made to block positive voltage and conduct positive current. I'm getting this that I'm using a transistor because that is what the transistor itself, the device, is used for. The device itself is to block positive voltage and to conduct positive current. So because I'm doing these, that is how I know that I'm going to use a transistor as opposed to something else. So here we're using transistor. This concept of choosing the device will become more clear once I do the second switch. So let's do switch B. Let's turn switch B on and then have A off. Now coming up here, we know that the current going through IB is going to be the same as the current through the inductor, right? Because our IB is defined up here, IB, and it's in the same direction as IL, right? So our polarities are the same. So we can define that as being positive. IB is positive. Okay, and then let's go to the next case. Switching this off, and then A is on. So now, switch B now has to block what voltage? The switch B has to block the generator voltage. But we have defined our voltage at the switch to be minus here and plus here. So our VB must block what? It must block a negative VG. It's blocking a negative voltage. So in this above case, the switch A, you're blocking both a positive voltage and you're conducting a positive current. But in this case, we have what? We're blocking a negative voltage and we're conducting a positive current. We have a positive on-state current, a negative off-state voltage. So then where are we? Where are we on this graph? We're in the second quadrant. So in the second quadrant, you have to use a diode. So this is just a quick conceptual summary on like how you're going to choose your devices depending upon your on-state current, your off-state voltage, and what kind of circuit that you have. Everything that I'm talking about is only built upon the buck converter. So if you're having a completely different circuit, it's going to be the same process. You're looking at the on-state current, the off-state voltage, but you're going to be computing these currents probably not as simply as we did just now. So I hoped that this has been helpful in kind of giving you a really high level overview, and hope you will join me next time. Thanks. Bye.